Okay, so here we have our triangle A and our triangle B, which we already know that they are similar triangles by a factor of 2. Um, and let's focus on some ratios here that we're going to be working on. So as I said before, we know that this angle X is going to give us which ones are going to be our opposite adjacent sides. The hypotenuse remains the same. Agree? So before we go into the ratios, I'm going to name them here because it's going to make our life easier. So according to this um, angle X, this side AB is going to be our opposite side. So I'm going to put it here. This one is our opposite side. This side here is our opposite side. And the one that is attached to it is going to be, oh, why? Let me just change this, girl, sorry. Okay, this one is going to be our adjacent side and our, perfect, and our hypotenuse remains to be the same. Perfect. And in our triangle B, same thing here. This is our hypotenuse. Our opposite side is this one, DE, and our adjacent side is this one. Fantastic. So if I want to find these ratios that I have here for my triangle B, opposite over hypotenuse, if I want to find that ratio, what it is. So if I do opposite is 3 over hypotenuse is 5. Can I simplify that ratio, that fraction even further? No, I can't, so I leave it like that. Okay, now let's look at this ratio. Adjacent over hypotenuse, so adjacent is going to be 4 over hypotenuse is going to be 5, and I can't simplify any further, so I'm going to leave it like this. And now let's look at the last one, opposite over adjacent. So opposite is 3 over adjacent, which is 4, and I can't simplify any further, so I'm going to leave it like that. Perfect. Now let's focus on our triangle B. So in our triangle B, I have opposite over hypotenuse. What do I have? What is my opposite? My opposite is 6 over my hypotenuse is 10. Can I simplify that fraction? Yes, I can. So I divide both numerator and denominator divided by 2. And that gives me that is equal to 3 over 5. Fantastic. Adjacent over hypotenuse, if we do this, so it's going to be 8 over 10. Again, can I simplify that fraction? Yes, I can. I can divide both numerator and denominator by 2. And this becomes 4 over 5. And opposite over adjacent, so it's going to be 6 over 8. And again, can I simplify it further? Yes, I can. So it's divided by 2, divided by 2, and that's going to become 3 over 4. Okay, first thing that I want you to notice, and maybe you already have seen that, it makes sense that if I started with this triangle A and I enlarged it and I made the next similar triangle by multiplying its side by 2, that's what we did when in the previous section. Agree? It makes sense that to simplify all these fractions, I had to use that same factor, and I always have to divide it by 2. So it does make sense. That was the first thing that I wanted to notice. And the second thing that I want you to notice is that these ratios, when I'm doing opposite over hypotenuse on both similar triangles, are the same, 3 over 5. And adjacent over hypotenuse is 4 over 5 here, and it's 4 over 5 here. And opposite over adjacent is 3 over 4 here, and 3 over 4 here. Okay, fantastic. These ratios that we're working here have special names. So I have written them down here, but I'm going to introduce to you these names. So what are these special names? So when we're talking about the um, opposite over hypotenuse, this is going to be called sine of an angle. And that angle is going to be our reference angle that help us to identify which one was going to be our opposite side and our adjacent side. You know what? In this case, I was calling it x. Oh, why did this happen? Let's do it again. Sine of x. Why did I decide to change it and not leave it as theta? Because in the diagram that I had above, the reference angle, which was this one that we had here, was x, and here was x. So I have to be coherent. I'm using the same symbol that I had here in the graph. This angle was named x, so that's why I'm saying that over here, I'm saying the sine of x is equal to opposite over hypotenuse. The special name that we use for this other ratio, our second ratio, is called cosine. So the cosine of x is equal to adjacent over hypotenuse. And the last ratio, special trigonometric ratio that we're going to learn today, is called tangent. And the tangent of x, is equal to the opposite side over the adjacent side. Okay? Now, this is known as SOHCAHTOA. I'm going to write it down. So, maybe I should do something else. Let me just. I'm going to use the colors that I'm using. So, it's going to take a little bit longer. Just bear with me. So, ka, so, ka, toa. And this is going to help you remember these trigonometry ratios. So SOHCAHTOA, perfect. So refers to sine, which is equal to opposite over hypotenuse. Then ka refers to cosine, which is equal to adjacent over hypotenuse. And then toa, which is tangent, which is equal to opposite over adjacent. So SOHCAHTOA will help you to remember those trigonometry ratios. In your book, they had a picture that I put it here. In case that this helps someone to remember those trigonometry ratios, they had like this music notes. So SOHCAHTOA, and they have here the little triangle with the theta in reference. So again, if this one is theta and it's our reference angle, then that means that the opposite side is across. Is this one is theta, our reference angle, then the adjacent, the one next to it is A, and the same here, theta, and then we have opposite and adjacent, and the hypotenuse is always the same, is always the longest side of that right angle triangle. Great. Your book has an interactivity when it's talking about trigonometric ratios, and I just wanted to show you something. So we have here our three trigonometric ratios: sine, cosine, and tangent. So sine of theta, we can see that we have here our angle theta. So if this one is our angle theta, then this one is going to be our opposite, and this one is going to be our adjacent, and our hypotenuse is always going to be the same, AB. Okay, so BC is adjacent, and AC is going to be opposite. Okay, so if we're talking about sine of theta, so means that sine of theta is opposite over hypotenuse. So opposite is going to be AC. We can say here that AC, they're saying that that is equal to 100. And then our hypotenuse is AB, that which is here, AB, that hypotenuse, which is 223 and 61 hundredths. And they have that they have it as a decimal when they do that ratio, and they found that that ratio was 447 thousandths. So we can play with this triangle. We can make here similar triangles. I'm going to move it. Okay, there you were able to see. So you can see that I have my side AC, now it's PQ, okay? And that PQ is my opposite side in reference to that angle theta. Notice that the angle theta hasn't changed. No, notice that the right angle triangle hasn't changed. Therefore, I'm sure that this angle, which is BPQ, is the same as BAC. It has to measure the same. Therefore, these triangles are similar. And this is what I want you to see here. You can see here that they're also calculating that ratio of sine of theta, and they have here PQ over PB. Notice how the magnitudes of PQ and PB are changing, but the ratio remains always the same. The sign doesn't change. So I want to make this triangle bigger. As I'm making it bigger, you can see that PQ is increasing and PB is increasing, but the ratio remains the same. And if I go and make them smaller, you can see that the magnitudes of the sides are changing, but the ratio remains the same. Okay, and if you don't trust your Jacaranda book and you want to verify, you can stop at any place and do this division in your CAS and see if you get to the same answer. If we go and we try it with the cos, we can see that cos, okay, we have left the same reference angle, so now we're going to be talking about co, so ka, toa. So ka, toa, ka is going to talk about the adjacent side. So it's going to be BC over AB. Agree? And with my similar triangle is going to be BQ over BB. Okay, and notice the same thing. We have here that the largest triangle BC is 200 over the same value that we have over the hypotenuse, and the ratio is given us that is 894 thousandths. When I start making my similar triangle smaller, again the magnitude of those side lengths is reducing, but the ratio remains the same. Okay, perfect. And the same is going to happen with tangent. So tangent is going to be opposite over adjacent, and what you can see here, they're playing with AC is 100 and BC is 200. So the ratio is 5/10, and the ratio is going to remain the same when we are playing with our similar triangle, making it bigger or making it smaller. The magnitude of the side lengths change, but the ratio remains the same. Fantastic.